To say has been one of the easiest students I've had to teach because he actually came to us with a doctorate in civil engineering from China and is getting his engineering degree so that he can obtain professional registration in the U.S. Is that correct?
Yes.
Yes. And so Wen's been one of our best students, still maintaining a 4.0, I believe. And like I said, it's been a breeze and a pleasure to have Wen as a student here. So without further ado, Wen Guo. Dr. Wen Guo.
First, thank you all for coming. And my name is Wenjun Guo, and the project I'm working on is a preparation and paint shop electrical design. So before I start, I would like to thank many people here who helped me during the past 2.5 years. And thanks Dr. Cuban, and helped me every step along the way. And it took an hour just to get my paperwork through, so I really appreciate your patience and the direction. And thanks Dr. Deersing, Dr. Schultz, who's not here, and hope he's doing good, and Dr. Davis, Dr. Smith, and Dr. Mitchell. I really enjoyed the learning experience here. And thanks Donna for getting everything organized. And the last thing, thanks my wife and the 3 boys letting me do this. I forgot to ask her permission to do this, but she forgave me later on. And this project is the preparation and painting shop. It's about 150. It's 150 feet wide, 150 feet long, 80 feet wide, 35 feet tall metal building. The scope work, including the general electrical load requirement, the lighting system design, the special equipment circuit design, and also we tie them together using that's the distribution system design. And here's some background of this project. Here's our current painting shop. It's about 50 feet by 50 feet. The largest piece we're painting is about 10 feet by 10 feet by 40 feet long. So we're constantly moving things in and out of the paint shop. It wastes a lot of money. Our cost, about more than 30%, is material handling. So we really need a bigger facility to make ourselves competitive in this market. So that's the new painting shop. You can tell the difference of the size. And this is the plan view, enlarged plan view of the painting shop. On the left-hand side, that's the preparation area. If a small part we can put in this painting booth, it's a self-contained paint booth. If it doesn't fit in the paint booth, we'll put in this the large painting area. And that's pretty much the size of the largest equipment we're going to paint, about 10 feet by 40 feet. It's pretty heavy, so we also need a brake crane to move this thing around the inside of the shop. And here's the section of the shop. This is the paint booth. We have air makeup units, and there's 2 brake cranes running across the building, and there's the exhaust fan to vent the large paint area. Again, that's the scope work. So first we need to do is the general electric load design. That's basically the receptacle of the shop. And the code asks us to design for a single receptacle for 180 volts amp. So if we have a 20 amp circuit, we need to calculate how many receptacles we can fit on one circuit. So for this calculation, we assume we leave a little bit of wiggle room here, so we use up to 80% of the circuit capacity. So that leaves us about 10.7. So we put 10 or 11 receptacles on the same circuit. It won't overload the system. And once we get the number tied down, we can lay out the receptacles around the perimeter of the shop. There's no code requirement for the industrial and commercial building in terms of the distance between the receptacles. But there's the general requirement for residential building. If you look at a house, the space maximum 12 feet on center. So we think it's a good rule of thumb to follow. That's how we lay out the receptacles here. There's the roll-up doors on both ends. That's why you see we skip the, so we can't run a receptacle in that area. And so we tie all the receptacles together, and this is the enlarged picture of this portion here. So we tie them together, then this home run connect to the electrical panel. You see the number here, the first one is the panel number. And it's a three-phase circuit, so you see that the circuit number here. So later on, you will see how we tie this number to the panel, just like your home. You open the electrical panel, you will see the circuit number. If something doesn't work, you can tell which breaker is supposed to work on. So that's the general electrical load requirement. The next one will be the lighting system design. The input for the lighting system is basically the geometry, the size of the building, where is the working surface. For this one, our working surface is 30 inches above the floor. And we use Philips lighting, the fluorescent lighting. And each lighting fixture has 26,800 lumens. So that's the light coming out from the lighting fixture. But it doesn't mean that all of them are going to reach the working surface, because they're going to dissipate it in the space, reflect it somewhere. So we have applied some knockdown factors to get the actual lighting we need. So the first one is called the coefficient of utilization. Basically, they divide the space into the whole building into three spaces: the space above the lighting, the space between the lighting and the working surface, and the space below the working surface. Based on that ratio, you can find out the coefficient of utilization. So for this one, we have 43%. So that means if lighting coming out of this lighting fixture, only 43% of the ratio working surface. That's the one you need to use. And the lighting is going to deteriorate over time. There's some of them burn out, and the dirt will cover some of the lighting fixtures. So you apply another knockdown factor. That's 60%. And for this type of application, we need a 35-foot candle. That's the lighting level we need to do the our preparation work. This room here, if you look at the surface here, probably give you about 30-foot candle. That's the lighting level what we're looking for. And based on the lighting fixture capacity, the level we need, the square footage of the space, this is the lighting fixtures output knockdown factor. We can calculate how many lighting fixtures we need in the whole building. And again, we need to tie all the lighting fixtures together, make sure we don't exceed the circuit capacity. And here's the how we run the circuit back to the panel. Again, this is the fluorescent lighting. We tie to the switch, and this is the home run back to the panel. And this is we use a single panel for all the receptacle and lighting load. And here's the enlarged portion of the lighting panel. The first column, the circuit number, that's the one we just saw on the layout drawing. And that's how many lighting fixtures on that circuit, and how much the voltage amp per circuit. So we're trying to balance them, so make sure all three phases are roughly equal. You don't want to heavily load one phase, and then you have a large neutral current coming back to the panel. So now we're done with the general electrical load lighting system. The next one will be the special equipment design. This is the preparation and painting shop, basically industrial application. There's a lot of special equipment inside of the building we need to supply power to. And there's the paint booth. We'll buy the paint booth from a vendor. Will come with a self-contained unit, but we need to supply the power. So we just assume we're going to have a single panel to supply power to this paint booth. Then there's the roll-up doors. There's the bridge crane, compressor on the outside. We use a lot of pneumatic tools. We need air compressor. And we also have exhaust fan for the large paint area. To give you one example, for the bridge crane, it's a three-phase 480-volt system. 34.6 horsepower. That's the current we need. And based on that current, we will be able to size the wire we need to allow the current to go through the system. So we need three number 4. That's the wire, and the one number 6. That's the neutral, the grounding wire coming back. And we'll run this directly from the power supply. We'll dig a trench, embed a PVC pipe, so we run this thing direct to the frame. So this drawing shows we call the raceway. So basically how you run your wire from the service entrance to the equipment you need. The one we just look at is our service entry from this point down. So we have the 1-inch PVC all the way up to here, and to supply the power for the brake frame. And this is how we run the wire for the other equipment. You see the solid line that mainly serves the roll-up door. That's the metal tubing we run above the ground, just around the perimeter of the building. And this dashed line indicates the PVC pipe will be buried underground. The reason we run it this way is because we can reduce the length of the run. If you have a too long a run, you have a large voltage drop. Just for the wire itself, you can damage. If you have too much voltage drop, you can damage the equipment itself. So we're done with the general electrical lighting system and special equipment. And the last one will be a distribution system to tie them together. And here's the single line diagram. We have the power entrance here, and a transformer here to supply power to the lighting and the receptacle panel. And there's another transformer to supply the paint booth. And there's other special equipment like motor, compressor. Will have this dedicated circuit. And the last thing we need to check is for all the transformers, we need to check the short current circuit. If there's a fault happens at a certain equipment, there will be short circuit through the whole system. And the system, the breaker and the fuse can protect the system, and it takes time for them to trip. So you need to design a system to withstand that short period of the short circuit current. And for our, we do it just for one transformer. That's the rated current capacity of that transformer, 600 amp. You divide it by the impedance of the transformer. That gives you the available short current circuit at the transformer itself. That's 17,000 amp. So you can tell the difference. And the fault can happen at the equipment, not at the transformer. So there's a wire running between them. So we need to deduct those loss at the wire. And also we need to consider some of the motor may contribute additional current to the system. So after the adjustment, we got 17,854 amp. That's a short current circuit. When we pick the circuit and fuse, we need to make sure they can withstand this short current circuit. Economic consideration is about 160 hours engineering and drafting, and the cost of the project is approximately $3.5 million. It's over the budget, so we need to value engineering to see what we can do to reduce the cost. So here's the conclusion. We did the general electrical load design, lighting system, special equipment, distribution system. We tie them together, and we generate a full set of electrical drawings for construction. And some of the recommendations, selection of the voltage. Also lighting fixtures can be powered from 120 volts. They also can be powered from higher voltage level, say 240, 277. If you use higher voltage level, you can lower the current, make the wire smaller. But if you have too many different levels of voltage, then you have too many transformers, panels, so you have to compromise. Either you invest in the wire or put more panels. And the lighting fixture, we use fluorescent light because we have this, we use the fluorescent lighting fixture for the whole facility, not just this building. So we think that if one of them burn, once a year we'll go there, replace all of them. If they're not burned out, we use on other buildings. But now the LED lighting is more and more cost effective. It's still more expensive at the front, but they can save you long term, they can save you some energy and the cost. So that's something we needed to do some study. Basically just initial investment versus long-term cost saving. And we still need to finalize all the design, make sure we coordinate with all the other disciplines, the structural, the mechanical, make sure we get all the roofs done, tied out. So that concludes the presentation. Any questions? All right, thank you very much for coming.